So folks, in this video we're continuing our definitions for classifying ODEs. And this is difficult right now because there's a whole bunch of different ODEs out there, and we are just beginning our discussion and learning to distinguish between different ones. At this point I assume you know what the order of an ODE is, the highest order derivative term in the equation. I assume you know what that is. And in the previous video we went through what a linear ODE was. The next definition that I want to give is, when is an ODE said to be in normal form? Remember that an ODE is an equation involving y, or a dependent variable, and some of its derivatives up to a certain order, and possibly the independent variable. Sometimes that's used as x or t. It could be another independent variable. So we're going to say that an nth order, we know what that means, an nth order ODE, we know what that means, is in normal form. That's what we want to define here. What do we mean by normal form? An nth order ODE is said to be normal form when it's written in the form y sub, that's the highest derivative we see here. Notice we see y prime, we see y double prime, but the highest order derivative that we see in this whole expression is n. So if you've isolated the highest order derivative term, then you're in normal form. So let's go ahead and look at this. This should give us a good intuition for this. This ODE right here, notice this is a third order ODE. Not necessary for this problem, but it is also linear. You could rearrange it into linear form like we did in the previous video. But notice our definition didn't state whether or not the ODE had to be linear. So the highest order derivative term is a third term. So if we go ahead and isolate that third derivative, then we've put it into normal form. So let's go ahead and do so. If I first go ahead and subtract over all of the other terms from this side, we would have y plus 3 plus the sine of x minus y double prime. And if we divide through by the variable x, we would get y triple prime is equal to y plus 3 plus the sine of x minus y double prime, all divided by x. And we've now isolated the highest order term, so this is in normal form. This right-hand side is a function. It's an expression that function, but it depends on three variables. 4 variables: x, y, y prime, and y double prime. And that's this function right here on the right-hand side. And so there we've identified as we were asked to do. This question asks, can this ODE right here easily be put into normal form? And you should try to solve for this. You can. You would get y to the third is equal to, and here we'd have not a function any longer, plus or minus the fourth root of negative x sine of y. And so we could rewrite this as y triple prime 1 of x is equal to plus the fourth root of negative x sine y, and y triple prime 2 of x. So we break it up into two separate functions. But I would argue that this is difficult. Yes, but messy. And certainly we can't represent that right-hand side as a single function. This is not a function. So I guess it's maybe up to interpretation whether you consider breaking this up into two separate functions. Having done so, maybe you could put some restrictions on both x and y so that it is well defined. But here we get to the point of this. Can all nth order ODEs be put into normal form? The answer is no. So sometimes we might want to talk about an ODE, but we will only talk about it if it can be written in normal form. Again, folks, if you're finding these definitions overwhelming, please don't worry about this. We've got the whole semester to get familiar with them. It's just that I want to be able to say we introduced all of these terms in the first week for you to have a place to go back and refer to them.